A sea-skimming anti-ship cruise missile breaks the radar horizon 5 nautical miles from the hull, screaming through the damp ocean spray at Mach 2.5. Low, fast, and dead set on total mass destruction, the weapon hugs the white crests of the waves to hide inside the ocean noise. The surface ship has less than 8 seconds before catastrophic impact. At that terrifying velocity, human reflexes and manual tracking are completely useless. A radar operator watching a screen cannot physically perceive the danger, calculate a complex target path, and press a firing button before the heavy warhead rips through the steel hull. The ocean offers no second chances when a high-speed missile closes the distance in the blink of an eye. This unforgiving countdown is why the Mk-15 Phalanx close-in weapon system was built. Known across the global fleet as the CIWS, the unit takes total autonomous command of the ship's final defense line the moment it is set to automatic mode. It does not ask for operational permission, wait for command confirmation, or hesitate when danger appears. The computer instantly evaluates every contact moving near the vessel, checking its incoming velocity, radar cross-section, and flight altitude. If an approaching object matches the trajectory profile of an incoming threat, the system tags it as hostile and locks on immediately. Autonomous authorization removes human delay from an equation where every single millisecond decides life or death. Popular culture often treats the Phalanx as a simple automated turret that blindly sprays lead across the surface of the water. The cold engineering reality of the machine is far more calculated and sophisticated. It is not a broad wall of random bullets, but a highly disciplined precision platform designed for complete physical target destruction. At its core, the system links a dedicated tracking radar directly to a 6-barrel M61 Vulcan gatling gun. By continuously measuring the exact trajectory of its own outgoing rounds against the moving position of the target, it makes thousands of instant corrections. This closed-loop fire control process guarantees that massive kinetic energy strikes the exact same point in space. This radical engineering shift was born from bitter historical lessons on the high seas. In 1967, Soviet-built Styx missiles struck and sank the Israeli destroyer INS Eilat, shocking naval commanders around the world. Traditional anti-aircraft guns directed by human crews prove completely helpless against fast, sea-skimming threats, exposing a critical vulnerability in modern naval defense. Naval architects quickly realized that human gunners could never match the closing speed of modern guided weaponry. Engineers at General Dynamics began developing a fully automated point defense assembly capable of detecting and engaging targets in milliseconds. The total failure of conventional shipboard artillery created the urgent military need for a self-contained mechanical guardian for the modern fleet. The physical structure of the Phalanx mount reflects this cold, survival-first design philosophy. Built as a single self-contained pedestal, the unit houses its search radar, Q-band tracking radar, fire control computers, and heavy ammunition drum in one unified assembly. Standing on the open deck, its white composite dome looks stark and solitary, yet it carries the entire burden of shipboard survival. Because the unit is completely self-contained, it requires only basic electrical power and seawater cooling from the ship beneath it. This modular bolt-on design allows any combat vessel to gain a last-ditch defensive envelope without rebuilding its primary combat systems. On a dark night in dangerous waters, crew members look to that silent white pedestal as their ultimate line of protection. Within a warship's layered defense network, the system occupies the absolute inner ring of protection. Long-range surface-to-air missiles attempt intercepts dozens of miles away, followed by medium-range weapons as the threat closes in. If those outer layers fail or are bypassed, the incoming missile enters the final lethal zone where only hard kinetic stopping power remains. This final engagement zone lies between 1,500 meters and 100 meters from the warship's hull. Within this tight operational window, there is no room for tactical maneuvering or second chances. The incoming target must be completely shredded and destroyed in midair before its shattered kinetic debris crashes directly into the ship's bridge or combat information center. The kinetic core of this defense is the heavy M61 Vulcan rotary cannon. Electric drive motors rapidly spin its 6 barrels, firing heavy 20mm armor-piercing projectiles at a rate of up to 4,500 rounds per minute. Each heavy round exits the barrel muzzle at over 1,100 meters per second, creating an unbroken stream of dense metal. That extreme rate of fire delivers 75 heavy tungsten or depleted uranium rounds every single second. As the weapon locks on, the night sky fills with a roaring curtain of metal engineered to smash the incoming missile to pieces. In those final critical seconds, the system transforms raw electrical power into an inescapable wave of terminal destruction. Sitting directly above the rotary cannon rests a distinct white dome housing the system's dual radar sensor package. This unit operates within the Q-band frequency spectrum, spanning 12 to 18 gigahertz. At these high frequencies, the shortened radar wavelengths produce exceptionally sharp beam widths. This allows the system to achieve extreme angular resolution, mapping the exact physical location of a high-speed target in three-dimensional space at close ranges. By mounting both the search and tracking radar antennas on the same stabilized platform as the gun, engineers eliminated the alignment errors that plague ship-wide defense networks. Traditional systems suffer from structural flex and sensor offset, requiring complex mathematical corrections. Placing the primary radar sensors directly on the gun mount ensures that the sightline of the tracking antenna remains rigidly aligned with the physical bore sight of the barrel assembly. Choosing the Q-band frequency spectrum introduces a sharp tactical compromise dictated by physics. High-frequency radio waves interact aggressively with water droplets in the atmosphere. Rain, ocean spray, and dense fog absorb and scatter the radar's emitted energy, causing rapid signal attenuation over extended distances. At ranges beyond 10 kilometers, atmospheric moisture degrades the radar signal so severely that distant detection becomes nearly impossible. For a point defense platform operating in the final layer of shipboard survival, long-range detection is entirely unnecessary. The primary mission demands millimeter-level precision within a localized 2-kilometer bubble rather than early warning across the horizon. By sacrificing long-range performance, the Q-band radar gains the razor-sharp spatial accuracy needed to track incoming anti-ship cruise missiles smaller than a human arm. Operating near the ocean surface creates another severe electronic challenge known as sea clutter. Wind-driven ocean waves reflect radar energy back into the receiver, generating massive false targets and multipath interference. A basic radar system attempting to scan near the horizon becomes overwhelmed by these chaotic water reflections, blinding its tracking sensors to low-flying threats skimming just meters above the water. To overcome this environmental noise, the Phalanx radar relies on advanced pulse Doppler processing algorithms. The system continuously measures the frequency shift of returning signals to determine target velocity. Static waves and slow-moving ocean surface clutter are instantly filtered out by the signal processor, leaving only fast-moving targets highlighted against the background interference. An incoming missile flying at supersonic speed is instantly isolated from the rolling sea beneath it. The mechanical choreography of target acquisition occurs in fractions of a second. The continuous search radar antenna spins at 90 revolutions per minute, sweeping 360 degrees around the warship. The instant its electronic beam detects a high-velocity target approaching on an attack vector, the computer threat analyzer calculates the target's trajectory and immediately hands off coordination data to the narrow-beam tracking radar. Within a split second of handoff, powerful electric drive motors slew the entire weapon mount toward the incoming threat. The monopulse tracking radar locks onto the nose of the missile, continuously transmitting location updates to the fire control computer. The speed of this mechanical and digital handoff eliminates human reaction delays, aiming the 6 barrels of the M61 Vulcan directly into the path of the approaching missile before a crew member can even read the alert screen. Once the weapon system engages, it activates a revolutionary targeting technique known as closed-loop fire control. Conventional anti-aircraft artillery fires based on predicted target position, hoping calculated lead distance matches real-world flight paths. The Phalanx operational logic functions differently. The tracking radar does not merely track the incoming anti-ship missile. It simultaneously tracks the dense cloud of outgoing 20mm armor-piercing rounds fired by its own gun. By processing radar returns from both the incoming warhead and the outgoing stream of projectiles, the fire control computer evaluates the actual trajectory of the bullets in flight. It compares the physical path of the projectile stream against the predicted intercept point of the target missile. This dual tracking capability transforms the gun from a blind shooter into a self-correcting feedback loop that adjusts its aim during active fire. As the stream of high-velocity tungsten rounds tears through the damp sea air, the radar measures the exact angular error between the target position and the center of the bullet cloud. It calculates the offset in real time, detecting microdegree variations caused by air density, thermal drift, or ship motion. There is no need for optical spotters or external telemetry to confirm impact. The fire control computer immediately feeds these positional corrections to the high-torque mount motors, adjusting the gun's physical alignment while the cannon continues to fire. The system literally walks the stream of dense metal projectiles onto the incoming threat. Within fractions of a second, the error vector shrinks to zero, locking the continuous curtain of armor-piercing rounds directly onto the missile airframe. At the mechanical heart of this system is the M61 Vulcan gatling gun. Driven by powerful hydraulic or pneumatic motors, the 6-barrel assembly rotates continuously during engagement to split the extreme friction and heat load across multiple barrels. The mechanical drive guarantees a rapid rate of fire, clearing the weapon chamber and feeding fresh rounds with continuous mechanical reliability during high-stress operations. Feeding ammunition to a cannon firing at 75 rounds per second presents intense mechanical challenges, especially when the entire mount is slewing violently to track a high-speed target. The system uses a dual-feed linkless ammunition handling system contained within a drum beneath the mount. By eliminating traditional flexible metal links, the mechanism prevents jammed casings during rapid movement, guaranteeing an uninterrupted flow of heavy rounds directly into the spinning breech. The lethality of the Phalanx depends directly on the physical composition of its ammunition. Early versions relied on the Mk-149 sub-caliber projectile, which used a high-density depleted uranium penetrator inside a plastic sabot. When fired, the lightweight sabot stripped away in flight, allowing the ultra-dense core to maintain maximum velocity and kinetic energy across its intercept vector. Modern fleet updates shifted the system toward the Mk-244 enhanced lethality cartridge, replacing depleted uranium with a heavier tungsten alloy penetrator. This specialized round increases the physical mass of the penetrator by 40% without changing the cartridge dimensions. High-density metal is essential because defeating a hardened anti-ship missile requires punching cleanly through heavy titanium skin and solid structural frames. Unlike anti-aircraft missile systems, Phalanx does not use proximity fuses or high-explosive fragmentation warheads. The mechanism relies entirely on direct kinetic impact to destroy incoming threats. Firing thousands of heavy tungsten darts into a target creates massive structural failure, shearing wings, shattering flight control linkages, and severing essential internal fuel conduits within milliseconds. At extreme velocities, kinetic transfer often detonates the missile's explosive warhead in mid-air through sympathetic shock. Even if the main warhead does not detonate immediately, disrupting the missile's airframe forces the heavy weapon into an immediate aerodynamic stall, causing it to tumble harmlessly into the ocean before reaching its target. This intense kinetic output creates severe mechanical friction and extreme thermal stress across the barrel cluster. Firing hundreds of heavy tungsten rounds in seconds generates rapid thermal expansion that can erode the barrel rifling and alter the inner alignment of the barrels. Uncontrolled heating drastically expands the bullet group spread, reducing the accuracy needed for precise intercepts. To manage these barrel heat dissipation requirements during sustained engagements, the computer enforces strict firing burst limits. Internal algorithms limit individual engagement bursts to short, calculated pulses, ensuring the barrels remain cool enough to prevent heat warpage or cook-off risks, while preserving tight bullet patterns against follow-on missile threats. These engineering lessons drove continuous structural upgrades through successive generations of the hardware. The original Block 0 baseline established the core autonomous defense system, but early testing revealed limitations in firing rates and operational processing speed. Engineers responded by redesigning the system architecture from the ground up to improve reaction performance. Block 1 introduced a pneumatic gun drive that pushed the rate of fire to 4,500 rounds per minute, while Block 1A integrated modular solid-state computers to accelerate threat evaluations. The modern Block 1B upgrade altered the weapon's appearance and capability, fitting longer barrels for tighter groupings and integrating advanced multi-sensor tracking packages. Real-world combat testing in coastal operations exposed critical gaps in early system programming. During the 1991 Persian Gulf conflict, chaotic radar environments and heavy chaff deployments created severe target tracking confusion near land. In one high-profile incident near the USS Missouri, complex surface reflections and background radar interference illustrated how coastline environments could blind legacy search routines. Waves bouncing off nearby land masses and surrounding naval vessels generated excessive ocean clutter that overwhelmed early signal processors. These early operations proved that autonomous air defense systems could not rely solely on basic Doppler radar signatures when fighting in shallow, heavily crowded littoral waters where false returns masked genuine incoming threats. To overcome these environmental blind spots, engineers developed the Block 1B update featuring the Phalanx surface mode. By mounting an optical forward-looking infrared sensor directly to the tracking assembly, the weapon system gained dual-mode targeting, allowing human operators to manually confirm and engage non-radar reflecting surface threats in real time. This optical integration expanded the platform's role into asymmetric defense. Using high-resolution thermal imaging, the weapon can lock onto fast inshore attack craft, low reflectivity unmanned aerial vehicles, and floating naval mines. The computer fuses infrared tracking data with radar telemetry, ensuring pinpoint kinetic fire even when targets produce minimal radar returns. Despite these advanced multi-sensor upgrades, close-in-point defense faces an unyielding physical reality known as residual kinetic momentum. When the cannon breaks apart a Mach 3 cruise missile at a distance of 300 meters, the threat's forward momentum does not simply vanish. The target turns into a cloud of supersonic debris traveling along the original ballistic trajectory. This disintegrating cloud of shredded airframe fragments, unburned fuel, and heavy structural pieces continues hurtling toward the vessel at supersonic speed. While the interception prevents a devastating main warhead detonation against the hull, high-velocity debris can still riddle the ship's superstructure, destroying radar arrays, communications gear, and unarmored deck equipment. This operational threat pushed the system off naval warships and onto dry land. In combat zones across Iraq and Afghanistan, military engineers adapted the naval mount into the land-based Centurion counter-rocket, artillery, and mortar platform. Mounted on heavy flatbed trailers, this mobile defense unit protected forward operating bases, tracking and intercepting incoming mortar rounds and unguided rockets mid-flight. Moving from open ocean to ground installations forced a complete redesign of terminal ammunition. High-density, armor-piercing penetrators that safely splash into deep ocean waters would shower nearby friendly personnel and civilians with deadly falling metal. Engineers solved this by switching to high-explosive incendiary tracer rounds designed to automatically self-destruct in mid-air if they miss the target, eliminating ground collateral damage. Despite these technical adaptations, the core platform remains constrained by a strict physical bottleneck during saturation attacks. The internal magazine drum holds a maximum of 1,550 rounds of ammunition. Firing at its maximum rate of 4,500 rounds per minute, the weapon drains its entire drum in just 20 seconds of continuous engagement. In combat, those 20 seconds translate to roughly 10 or 12 short burst engagements. When adversary forces launch simultaneous swarms of multiple incoming missiles, target acquisition latency becomes a fatal vulnerability. The processing radar must acquire, track, evaluate destruction, and slew to the next incoming threat in milliseconds, where a tiny processing delay can leave the platform completely empty. To counter magazine exhaustion and swarm saturation, modern naval architecture abandoned isolated weapons mounts in favor of fully integrated defense layers. Current combat systems link the Gatling cannon directly with rolling airframe missile launchers and fleet-wide tactical networks. Shared sensor telemetry allows shipboard computers to coordinate defensive responses seamlessly across multiple ship platforms. This cooperative network dynamic optimizes asset allocation during high-density combat. Long-range search radars detect air threats hundreds of miles away, allowing combat computers to prioritize targets based on incoming velocity and threat trajectory. Long-range surface-to-air missiles engage outer threats first, reserving short-range gatling fire strictly as an emergency final layer against anything breaking through. Yet even multi-layered fleet networks face severe physical limits against modern hypersonic anti-ship missiles. Flying in excess of Mach 5 on low-altitude boost glide or scramjet flight paths, hypersonic threats collapse reaction times down to near zero. The duration between initial radar detection and impact narrows to just a few fractions of a minute. At hypersonic velocities, mechanical tracking limits hit an absolute wall. Even when fire control computers process closed-loop corrections instantly, physical hydraulic drives and mechanical gears cannot swivel the heavy gun mount fast enough to match sharp evasive maneuvers. The physical movement of heavy steel components becomes the fundamental breaking point in kinetic defense. This physical boundary accelerates the modern shift toward directed energy weapons and solid-state lasers. Where rapid-fire cannons face barrel heat limits, mechanical wear, and finite magazine capacities, laser systems draw continuous power directly from shipboard generators. A laser beam reaches its target at the speed of light, bypassing lead distance calculations entirely, though fog and moisture still present atmospheric challenges. The long-term consequence of automated close-in weapon engineering extends far beyond hardware design. The cold realization that human reflexes were entirely useless against supersonic anti-ship missiles forced naval planners to rewrite military defense doctrine, permanently replacing human trigger fingers with automated algorithmic decision-making. Modern surface warships are now engineered from the keel up around these autonomous survivability rings. The fire control logic established by early close-in weapons created the blueprint for contemporary naval warfare, making machine autonomy an absolute baseline requirement for any vessel operating in contested waters. For the sailors stationed aboard these guided missile destroyers, this reliance on total automation creates a stark psychological reality. During anti-ship missile defense operations, human crew members become passive spectators, watching radar displays as automated fire control computers make instantaneous life-or-death combat choices on their behalf. Naval personnel must entrust their survival entirely to silicon processors and high-frequency radar algorithms. When incoming warheads close those final few thousand yards, human courage and training yield completely to pre-programmed logic gates, leaving ship and crew dependent on code written decades prior in defense labs. From early combat trials during late 20th century engagements to active missile defense operations in 2024 across the Red Sea, the evolution of autonomous close-in weapons proves that kinetic defense has reached its structural limits. As anti-ship missiles grow faster and stealthier, the gap between human military command and fully autonomous defense continues to close forever. The broader aftershock of this shift became clear in 2024 defense reports examining anti-ship engagements across the Red Sea. Military planners realized that the foundational assumptions of naval warfare had permanently changed. Survival no longer depends on human courage or traditional fleet size, but on the unyielding reaction speed of automated radar circuits. A single hardware delay or radar processing blind spot can now result in the total destruction of a multi-billion-dollar warship in a fraction of a second. Yet one critical question remains unsettled within modern military archives and combat records. As threat environments evolve toward swarms of low-cost drones and hypersonic strike weapons, defense analysts still debate whether physical gatling cannons have reached their absolute structural limit. No amount of software optimization can overcome the physical reality of an emptied magazine when dozens of incoming targets saturate the sky simultaneously. This leaves fleet commanders facing an unsettling dilemma for future naval encounters. Even as laser technology advances to support conventional hardware, the ultimate test of automated point defense remains unproven against coordinated, multi-angle saturation strikes. The unresolved question is not whether closed-loop radar systems work, but whether any close-in weapon can fire fast enough to save a ship when the sky fills with incoming fire. On the darkened deck of a modern destroyer, the white dome of the Phalanx stands in silent readiness, its radar continuously sweeping the night horizon. It remains humanity's final line of defense against incoming fire, a spinning assembly of steel and code, watching and waiting for a battle that will be decided in less than 3 seconds.